Here is a number to stop any systems engineer cold. In a six-figure agent skill ecosystem, enabling skills degraded performance on 15% of tasks. It gets worse. For at least one model tested, introducing skills produced zero improvement on 87% of tasks, while simultaneously inflating token usage by over 400%. The entire AI engineering space is placing a massive bet on a reusable, portable unit of code. But that unit is quietly breaking upon contact with different models. Adding explicit instructions to a large language model should not make it worse at completable tasks. This paradox points to a massive, unaddressed abstraction leak in our current agent architecture. You're watching Bearded AI Guy. I analyze AI agent research through the rigorous lens of a systems engineer, looking specifically for where the abstractions leak. Today, we look at SkVM. Its central thesis proposes a strict new architecture. Agent skills are code, and LLMs are the processors executing them. This matters right now because Anthropic's agent skills standard just went open source, and every major platform is racing to support it. Yet no one has actually proven that write once, run anywhere works for agents. Our objective today is to determine if an ahead-of-time compiler is the correct abstraction to fix non-deterministic agent behavior, or if standardizing agent skills right now is simply premature. Currently, a skill is deployed as a simple plain text folder. An agent loads the catalog, sees a name and description, and pulls in the full instructions only when a task looks relevant, a process called progressive disclosure. But look at what happens in practice. A plain text skill makes three silent assumptions. First, it assumes the model can follow its specific workflow. Second, it assumes the harness exposes the right tools. And third, it assumes the host environment contains the correct packagers. When any of those variables change, the code doesn't explicitly break, it just degrades. Shipping the exact same skill to two different agent harnesses running the identical model produces a hidden 13-point performance gap between them. Portability is not a binary state, it is a multivariable equation. Right now, developers are shipping code blindly, lacking any management layer to control the final capability outcome. Think of compilation like translating a recipe. You don't hand the same recipe to every kitchen. Instead, a compiler translates the requirements to match the specific tools and stove available without altering the intent of the original dish. Looking at the technical architecture here, we see that SkVM does not output a universal stable bytecode. Instead, the source document fans out into 6 distinct interconnected intermediate data structures. The system extracts what's called a skill capability requirement, or SCR, essentially what the code needs to run. It then measures that against a target capability profile, or TCP, which tests a specific model and harness pair across 26 primitive capabilities. Alongside these profiles, it generates a directed acyclic graph, mapping out execution variants, plus an idempotent setup script to strictly prepare the environment. The term virtual machine in SkVM is highly aspirational. The immediate technical reality is a compiler that produces an effective intermediate representation made entirely of data graphs, not executable binaries. The current industry standard is to hand the LLM the instructions and let it try its best. SkVM replaces that hope with a rigorous negotiation. This diagram illustrates a skill's required capabilities facing off against a target's actual capabilities, allowing the system to measure the precise gap between them. Once that gap is measured, logic kicks in. If the gap is small, the system compensates. If the gap is massive, it substitutes alternative computational paths. And if the gap is impossible to bridge, it degrades gracefully rather than failing silently. This negotiation happens through a sequential 7-step loop. This flowchart maps the process from offline target profiling at the top, all the way down to just-in-time variant selection at runtime. Pay attention to the compute overhead in the readout docs. Target profiling is a one-time computational cost per model and harness pair. It requires about 7.3 minutes for a model like Devstral and 31 minutes for Qwen 3. This reframes the deployment mindset. The operational question is no longer, does this skill exist? The question is, what specific transformed variant of this skill should this target be allowed to see? There is massive confusion right now conflating skill formatting, orchestration logic, and transport protocols. They execute entirely different jobs. To see how they interact, we can map the modern agent stack into 4 distinct layers. This diagram shows SkVM at the foundation, moving up through orchestration, MCP, and agent skills at the top. Starting at the top, agent skills purely govern metadata discovery and progressive disclosure. The layer below that, frameworks like LangGraph and CrewAI, strictly handle application orchestration and event flows. Then we have the transport layer. The Model Context Protocol, or MCP, standardizes capability negotiation, but it strictly negotiates with external, outside systems. SkVM isn't replacing any of those. It is inventing the missing bottom layer. It is the only system reasoning about the internal capability of the local model and harness pair executing the code. Let's look at the benchmark results. This dashboard illustrates the true victory of compilation, reliability. On the left, uncompiled skills show wildly divergent performance across harnesses, leaving a 13-point gap. On the right, compilation stabilizes that behavior, forcing the lines to converge to a tight 5-point variance. The data shows up to 40. The top layer will remain a clean, legible folder containing a simple package, but beneath it lies a complex web of optimized data bundles. High-volume platforms will adopt SkVM-like compilation out of sheer necessity. They will quietly run gap analysis and variant selection behind the scenes, while maintaining support for simple plain text folders on the front end. This is the mental model to carry forward. When you write a skill, you are authoring a legible contract. What the system actually executes is a highly optimized, target-specific artifact. If you want to understand the mechanics beneath the abstractions, subscribe to Bearded AI Guy. I'm tearing down the 2026 agent stack, paper by paper. Drop a comment below. Do you think portable skills will ultimately standardize at the package layer or at the bytecode layer? Credit where it's due. This research comes from the human architect, the author and engineering architect behind AI agents in action. The next time someone promises you skill portability, ask them the SkVM question. Portable between exactly which model and exactly which harness. Right now, the folder is the promise, but the compiler is the proof. I'll see you in the next one.